Place your hand on your chest right now. Feel that, your heart beating, once per second. You are made of time itself. This rhythm inside you has measured human life for millions of years, without ever needing to be wound. Tonight, we explore this and the quiet science of how we mark our moments. Settle in somewhere comfortable. Place your hand on your chest. Feel that rhythm, your heart beating steadily, once per second, sometimes a bit faster, sometimes slower, but always keeping time. This is the most personal clock you own, more reliable than any watch, more constant than any device. Your heart has been counting since before you were born. It will count until your last moment, each beat marking another second of your life. You carry roughly 60 beats per minute when you rest, over 3,000 beats per hour, more than 70,000 beats each day. This happens whether you think about it or not. Your body keeping perfect time without any effort from you. Ancient humans had no clocks, but they had this rhythm. They could feel their pulse, count their heartbeats, use their own body as a timer. Running a certain distance took a certain number of heartbeats. Holding your breath underwater, waiting for bread to bake, all measured in the steady drum of your heart. Your heart knows things before your mind does. When you see something frightening, your heart speeds up before you consciously feel afraid. When you relax, your heart slows before you notice the calm. This ancient timekeeper responds to the world faster than thought. Athletes use heart rate to measure effort, not by how tired they feel, by how fast their heart beats. The body telling the truth that the mind might miss. Your heart cannot lie about how hard you are working. The rhythm is not perfectly regular. It varies slightly with each breath. When you breathe in, your heart speeds up just a little. When you breathe out, it slows down. This variation is healthy, called heart rate variability, a sign that your body is responding naturally to the world. If this brings you calm, if you enjoy these quiet journeys through science, I would love for you to join our community. Hit that subscribe button. It helps more people find this peaceful space. And leave a comment telling me where you are listening from. What time is it there? I love knowing we are all scattered across the world, finding rest together in these small wonders. Babies in the womb hear their mother's heartbeat. This becomes their first sense of time, the rhythm they know before they know anything else. Some researchers believe this is why heartbeat sounds calm us, why we sleep better with white noise that has a pulse. We are returning to our first clock. Your heart beats faster when you are young. A newborn's heart races at over 120 beats per minute. As you grow, it slows. An adult heart settles into 60 or 70. This gradual slowing marks the passage of your life. Time measured not in years, but in beats. Musicians count time with their pulse when no metronome is available. Conductors feel the tempo in their chest. The body and music speaking the same language, both measured in beats per minute. Even when you sleep, your heart keeps counting. It slows down, but never stops, measuring the night in steady rhythm. Your body knows how long you have been resting. Your heart has counted every second. This is time at its most basic. Not hours or minutes invented by humans. Not seconds defined by scientists. Just the steady beat that has kept time since hearts first evolved. The rhythm that every human being carries. The clock that needs no winding, no batteries, no adjustment. Right now, your heart is beating, marking this moment, counting the seconds as you listen. This ancient timekeeper, doing what it has always done, measuring your life one beat at a time, keeping perfect time in the only way that truly matters. And somewhere in the quiet rhythm of your heartbeat, you can find a kind of peace. The knowledge that time is not something external, not something to chase or fight. It is something you carry, something that moves through you with every pulse, every breath, every moment of your existence. That heartbeat was enough for one person. But what about groups of people who needed to agree on when something would happen? They looked up. The sun was humanity's first shared clock. Everyone saw the same sun, watched it move across the same sky. This gave us our first way to coordinate time together. Ancient people noticed their shadows changed through the day. Morning shadows stretched long to the west. Noon shadows shrank to almost nothing. Evening shadows reached east. The shadow became a pointer, a hand on nature's clock. Someone had the idea to mark where shadows fell, probably in Egypt or Mesopotamia, around 5,000 years ago. They placed a stick upright in the ground, drew lines where its shadow reached at different times. This simple device could tell anyone what time it was just by looking. The sundial was born. These early sundials were not precise. They divided day into rough chunks: morning, midday, afternoon. But that was enough. Farmers knew when to break for meals. Traders knew when markets would open. Priests knew when to perform ceremonies. The stick that casts the shadow is called a gnomon. This word comes from Greek, meaning one who knows. The gnomon knows the time by reading the sun's position. It translates the sun's movement into information humans can use. Sundials improved over centuries. Egyptians carved elaborate stone sundials with 12 divisions for the hours of daylight. Greeks angled their gnomons to match Earth's tilt. Romans built pocket sundials for travelers, each culture refining this simple technology. The mathematics of sundials is beautiful. The gnomon must point toward the celestial pole, the North Star in the northern hemisphere. This alignment means the gnomon is parallel to Earth's axis. Now, the shadow moves at a constant rate as Earth rotates. The hour lines are not evenly spaced. They get closer together the farther from noon you go. This is because the gnomon casts a cone of shadow. When you slice a cone at an angle, you get these uneven spacings. The math accounts for your latitude. A sundial designed for Cairo will not work correctly in London. Sundials only work when the sun shines. Cloudy days left people guessing. Night was entirely unmeasured. Winter days were shorter, so the hours themselves were shorter. Summer hours were longer. Time was flexible, tied to the season. Some cultures divided night and day into 12 hours each. This meant winter daytime hours were short, and summer daytime hours were long. The length of an hour changed with the season. Time was not the rigid thing we know today. Sundials marked the first time humans externalized time measurement. Before, time was felt internally or observed in nature. Now, it was carved in stone, made permanent, given a physical form that would last generations. You can still see ancient sundials in museums. Stone circles with shadow lines, worn smooth by thousands of years. These objects connected people to the sun's rhythm, made time visible, shareable, agreed upon. The sundial taught us that time flows constantly. The shadow never stops moving. You cannot pause it, cannot save it for later. It simply passes, teaching an early lesson about time's nature. Even today, sundials have a place. Gardens feature them as decoration, but also as reminders that time once moved with the sun, that our modern precise clocks are very recent inventions, that for most of human history, this simple stick and its shadow were enough. The sundial was the first tool that let groups of people synchronize their actions, meet at an agreed time, coordinate work, plan together. This changed human society, made civilization possible in new ways, and on a clear day, you can make a sundial yourself. Place a stick upright, mark where its shadow falls each hour. By day's end, you have created the same tool that served humanity for thousands of years, your own connection to the sun's ancient clock. Somewhere right now, in some quiet garden, a sundial is telling time, its shadow creeping across stone, moving with the sun as it has for millennia, silent, patient, keeping time the oldest way we know. But the sun disappears, clouds hide it, night swallows it completely. People needed time in the dark. They turned to water. Water flows at a constant rate if the container is shaped correctly. This makes it perfect for measuring time. The Egyptians figured this out around 3,500 years ago. They called it a clepsydra, water thief, because it steals moments and makes them visible. The simplest water clock is just a pot with a hole in the bottom. Fill it with water. The water drips out steadily. Mark lines inside showing the water level at different times. As the level drops, you can see how much time has passed. But there is a problem. Water pressure. When the pot is full, pressure pushes water out faster. As it empties, pressure decreases and water drips slower. The hours at the top are shorter than the hours at the bottom. Ancient engineers solved this cleverly. They shaped the pot so it got narrower toward the bottom. Less water at the top meant less surface area, which compensated for the higher pressure. The shape made the flow constant despite changing pressure. Other designs used two pots. Water dripped from one into another. The receiving pot had hour marks. As it filled, you could read the time. The dripping created a gentle sound, a rhythm, time made audible. The Greeks refined water clocks into complex machines. Gears turned by the flowing water. Hands pointed to hour marks on a dial. These clocks looked almost modern. Mechanical time before anyone invented mechanical clocks. One famous Greek water clock had a figure that pointed to the hours. As water filled a chamber, it lifted a float. The float raised the figure's arm. The arm pointed to markings showing the time. Simple mechanics. Elegant solution. Water clocks worked equally well, day or night, in sun or clouds. This made them more reliable than sundials for many purposes. Courts used them to time speeches. Lawyers got a fixed amount of water. When it ran out, they had to stop talking. Time became fairness. The Chinese developed water clocks into astronomical instruments. Their clocks drove mechanisms that tracked star positions. Water flow measured not just hours, but the movement of celestial bodies. Time and space connected through dripping water. In cold climates, water clocks faced a problem. Water freezes. Some cultures used mercury instead. It flows like water, but does not freeze at normal temperatures. Others used sand. Though sand clocks are technically different, the principle is the same. A substance flowing at constant rate, measuring time's passage. Water clocks had to be maintained. Refilled regularly, the hole cleaned so sediment did not slow the flow. Someone had to watch them, tend them. This created jobs. Timekeepers. People whose sole purpose was making sure everyone knew what time it was. These clocks were not portable. You could not carry a pot of dripping water through city streets. Time stayed in one place. Public water clocks in town squares, private ones in wealthy homes. Time became architecture, a feature of buildings. The accuracy was impressive for the technology. A well-made water clock could measure time to within minutes per day. Not perfect, but far better than guessing. Good enough to organize society, schedule meetings, coordinate work. Monks in medieval Europe used water clocks to know when to pray. The night hours needed measuring. Sundials offered nothing. Water provided the answer. Drop by drop, the night was divided into prayer times. The water clock taught us that time could be captured in substance, that flow itself could be a clock, that the same physics that makes water pour from a jug can measure your life. Some museums have working water clocks now. You can watch the water level drop, hear the gentle drip, see hours pass in liquid form. It connects you to those ancient engineers who first understood that steady flow equals steady time. And tonight, somewhere in a demonstration or museum, water is dripping, marking seconds, measuring minutes, doing what it has done for thousands of years, turning the invisible passage of time into something you can see, something you can measure, something as simple and constant as water finding its way downward. Water flows downward, but something else moves with perfect rhythm, something swinging. Galileo noticed it in 1582. He was 19 years old, sitting in a cathedral in Pisa. A chandelier hung from the ceiling, swaying in the breeze, back and forth, back and forth. He watched it, timed it against his pulse, that heartbeat we talked about earlier. And he noticed something strange. The chandelier took the same amount of time to complete each swing, whether it swung in wide arcs or narrow ones. The time stayed constant. This should not make sense. A longer distance should take more time, but it does not. This is the secret of the pendulum. A pendulum is just a weight hanging from a fixed point. Gravity pulls it down. Momentum carries it past center. Gravity pulls it back. The weight swings eternally if nothing stops it, and each swing takes exactly the same time. The period depends only on the length of the string, not the weight, not how far it swings, just the length. A longer pendulum swings slower, a shorter one swings faster. But for any given length, the period never changes. This makes pendulums perfect for clocks. They provide a steady beat, a mechanical heart that never speeds up or slows down from excitement or rest. Galileo understood this immediately. He proposed using pendulums to measure time, to build clocks around this principle. But he never built one himself. That would come later. In 1656, a Dutch scientist named Christian Huygens built the first pendulum clock. It was vastly more accurate than anything before. Water clocks might be right within minutes per day. The pendulum clock was right within seconds. This transformed timekeeping. Suddenly, people could measure time precisely, schedule meetings to the minute, run experiments that required exact timing, navigate ships more accurately. The pendulum made precision possible. The mechanism is elegant. The pendulum swings. At the bottom of each swing, it pushes a gear tooth forward. The gear turns slightly. This gear connects to other gears, eventually turning the hands on the clock face. Each swing moves time forward by exactly one increment. But pendulums need energy. Friction eventually stops them, so clocks use weights or springs to give the pendulum tiny pushes, just enough to keep it swinging, Not so much that it swings faster. The escapement mechanism does this, releasing energy in tiny, controlled amounts. The escapement is crucial. It is what makes mechanical clocks possible. It controls the release of stored energy, so the clock runs at constant speed. Without it, the spring or weight would unwind all at once, and the clock would race forward uselessly. Pendulum clocks dominated timekeeping for nearly 300 years. Every accurate clock used them, from pocket watches too small to fit a pendulum, but using the same oscillating principle, to tower clocks with pendulums taller than a person. The rhythm became part of daily life. Tick-tock, tick-tock, the sound of time passing, a metronome in every home, every public building. Time made audible through the swing of a weight. Temperature affects pendulums. Heat makes metal expand. The pendulum grows longer and swings slower. Cold makes it shrink and swing faster. Clockmakers solved this with special alloys, materials that barely expand, or pendulum rods made of different metals that expand in opposite directions, cancelling each other out. Gravity affects them too. A pendulum at sea level swings slightly faster than one on a mountain. Gravity is weaker at altitude. This meant clocks needed adjustment when moved. Time became tied to location. The pendulum taught us that regular motion can measure time, that physics provides natural rhythms we can harness, that a swinging weight is as reliable as the sun or dripping water. Maybe more so. You can make a simple pendulum right now, a string and a weight. Any weight. Tie it, let it swing. Time the swings. You will find Galileo's truth. Each swing takes the same time. Physics keeping time through simple motion. And in some old clock somewhere, a pendulum still swings. Tick-tock, tick-tock, measuring seconds through gravity and momentum. The rhythm that revolutionized human timekeeping. That pendulum swings because of what is inside the clock. Gears and springs working together. Let me show you how a mechanical clock is stored time, energy wound up and waiting. You turn a key or pull a chain. This winds a spring tight or lifts a weight high, potential energy, ready to be released. The spring wants to unwind. The weight wants to fall. If you let them go freely, they would release all their energy in seconds. The clock would be useless. So, the escapement holds them back, controls the release. Picture a gear with specially shaped teeth. The escapement allows one tooth to move forward, then catches the next tooth, holds it, waits, then releases it, one tooth at a time. This clicking rhythm is the sound of time being controlled. Each tooth that escapes turns the gear slightly. That gear connects to another gear. The second gear might have more or fewer teeth. This changes the speed. Gears multiply or divide motion. One gear turning fast drives another gear slowly. A clock face has 3 hands typically. Seconds, minutes, hours. These all move at different speeds. 60 seconds per minute, 60 minutes per hour. The gears create these ratios. The second hand might connect to a small gear that turns a larger gear for minutes. That larger gear turns an even larger gear for hours. The math is simple but precise. If you want the minute hand to move 60 times slower than the second hand, you use gears with a 60-to-1 ratio. One gear with 60 teeth driving a gear with 1 tooth, or any combination that multiplies to 60. Old clocks needed winding daily. The spring or weight ran out of energy. Modern clocks might run for days or weeks. Better efficiency, less friction, stronger springs. But the principle stays the same. Stored energy released in controlled amounts. The The materials matter. Early clocks used iron and brass. These wear down, create friction, lose accuracy. Later clocks used jeweled bearings, tiny rubies or sapphires at friction points. These hard stones create almost no friction. The gears spin freely. The clock runs true for decades. Some clocks use balance wheels instead of pendulums. A wheel that rotates back and forth. Springs pull it one way. Momentum carries it past center. Springs pull it back. This oscillation is like a pendulum, but works in any position. Perfect for watches you carry. For ships at sea, where pendulums would not work, the balance wheel connected to a hairspring. A delicate coil of metal that winds and unwinds with the wheel's rotation. The spring provides the restoring force, pulls the wheel back to center. Together, they create the same constant rhythm a pendulum provides through gravity. Watchmakers became masters of miniaturization, fitting all these parts into something you could carry in your pocket. Gears smaller than your fingernail, springs thinner than hair, all working together, keeping time while you walked, while you rode horses, while you lived your life. The complexity is beautiful. Open an old pocket watch, see dozens of gears, each precisely cut, each perfectly positioned, all turning at their designated speeds, some fast, some slow, all synchronized to divide time into seconds, minutes, and hours. These mechanisms taught us that time could be mechanical, that physics and engineering together could capture something as abstract as time, make it tangible, put it in your pocket, carry it wherever you go. The reliability improved over centuries. Early mechanical clocks lost minutes per day. Later ones lost seconds per week. Modern mechanical watches can be accurate to seconds per month. Each generation of clockmakers solving tiny sources of error, reducing friction, compensating for temperature, perfecting the escapement. Even now, mechanical watches are valued, not because they are the most accurate. Quartz and atomic clocks are far more precise, but because they represent pure mechanics, time kept by gears and springs. No batteries, no electronics, just carefully shaped metal, working according to physical laws. Right now, inside thousands of watches and clocks, gears are turning, springs are unwinding, escapements are clicking, each one measuring time through nothing but mechanical motion. The elegant solution that served humanity for centuries. Those mechanical clocks measure time outside your body. But you have another clock, one that runs without gears or springs. Deep in your brain, the suprachiasmatic nucleus. Say that 3 times fast. It sits just above where your optic nerves cross. A tiny cluster of cells, about 20,000 neurons. This is your master clock. These neurons fire in rhythm. They create electrical pulses that rise and fall over roughly 24 hours. This rhythm happens even in complete darkness. Even if you are isolated from all time cues, your brain knows what time it is. This is your circadian rhythm. Circadian means about a day. The rhythm that tells your body when to sleep and when to wake, when to be hungry, when to be alert. It conducts your entire physiology like a symphony. Without any light, your rhythm runs slightly longer than 24 hours. About 24 hours and 11 minutes for most people. This means, without cues, you would slowly shift later each day. Go to bed 11 minutes later. Wake 11 minutes later. Over weeks, you would be completely reversed. But you have cues. The strongest is light. When light hits your eyes in the morning, signals travel to your suprachiasmatic nucleus. The light resets your clock, synchronizes it to exactly 24 hours. This happens every single day. Blue light is most effective. The blue wavelengths in morning sunlight. This is why sunrise is so powerful for your sleep cycle. Why looking at blue screens at night disrupts sleep. Your brain thinks the sun is rising, gets confused about what time it is. Your clock controls more than sleep. It regulates body temperature. Lowest around 4 in the morning, highest in late afternoon. This is why you feel coldest before dawn. Why fevers often peak in evening. It controls hormone release. Cortisol rises before you wake, prepares your body for the day. Melatonin rises as darkness approaches, makes you sleepy. Your clock conducts this daily dance. It even affects when you think best. Most people are sharpest in late morning, about 10 in the morning for early risers, noon for late risers. This is when your brain is most alert, most capable of complex thought. Your digestive system follows the clock too. It expects food at certain times. This is why eating at odd hours can upset your stomach. Why shift workers often have digestive problems. Their eating schedule fights their internal clock. Babies are not born with a mature circadian rhythm. It develops over the first months of life. This is why newborns wake at all hours. Their clock has not learned day from night yet. Around 3 to 6 months, the rhythm stabilizes. Parents finally sleep again. As you age, your rhythm shifts earlier. Teenagers naturally want to sleep late and wake late. Their clocks run delayed. This is biology, not laziness. Older adults tend to wake earlier, go to bed earlier. The clock shifts through life. Some people have naturally early clocks. Morning people, larks. They wake easily at dawn, feel tired by 9 at night. Others have late clocks, night owls. They cannot sleep before midnight, struggle to wake before 9. This is genetic, not a choice or habit. Fighting your natural clock is difficult. A night owl forcing themselves to wake at 6 will always struggle. Their brain says it is the middle of the night. A morning person trying to stay up late feels the same struggle. The clock resists. The rhythm affects everything. Your immune system, strongest in the middle of the night. This is when your body fights infections most effectively. Your cardiovascular system, blood pressure drops at night, rises in morning. Even your cells have circadian rhythms. Every cell has clock genes that turn on and off in 24-hour cycles. Your whole body is a collection of billions of tiny clocks, all synchronized by the master clock in your brain. This clock is why you feel jet lag, why shift work is so hard, why losing sleep on weekends, then trying to catch up, never quite works. You are fighting millions of years of evolution, a clock that expects regularity, that thrives on routine. Right now, your clock is ticking, measuring your day, preparing your body for what comes next. An invisible rhythm keeping time in every cell you have. That clock in your brain needs to be reset daily. Light does this, but not just any light. Your eyes contain special cells that have nothing to do with seeing images. They do not help you read or recognize faces. They only detect brightness. These cells contain a protein called melanopsin. This protein responds most strongly to blue light. When blue light hits these cells, they send signals directly to your suprachiasmatic nucleus, your master clock. The message is simple. It is daytime. Reset. Morning light is richest in blue wavelengths. Sunrise contains strong blue light. This is not accident. Your clock evolved to synchronize with sunrise. For millions of years, sunrise was the most reliable time signal available. When you see bright blue light in the morning, your clock shifts earlier. You will feel sleepy earlier that night. Wake earlier the next morning. This is how morning light helps night owls become morning people. The opposite happens with evening light. When you see bright light after sunset, your clock shifts later. You will feel sleepy later. Wake later. This is why staying up with bright lights makes it hard to wake early. The intensity matters. Bright light has stronger effect than dim light. Outdoor light is vastly brighter than indoor light. Even a cloudy day outside is brighter than a well-lit room inside. Your clock responds to this brightness. A typical living room might be 200 lux. That is the measurement of light intensity. A cloudy outdoor day is 5,000 lux. A sunny day is 10,000 lux or more. Your clock notices this difference. This is why people who work indoors often struggle with sleep. They never get enough bright light to strongly set their clocks. Their rhythms become weak, drift later. Sleep becomes irregular. Getting bright light in the morning helps everything. Makes you more alert during the day. Helps you sleep better at night. Improves mood. The simple act of going outside in the morning synchronizes your whole physiology. Evening light does the opposite. Screens emit blue light. Phones, computers, televisions. This blue light tells your brain it is morning, suppresses melatonin, keeps you awake when you should be winding down. Blocking blue light in the evening helps. Orange-tinted glasses filter out blue wavelengths. Let other colors through. Your clock sees darkness even while you see the screen. Melatonin rises normally. Sleep comes easier. Some cultures understood this intuitively. Candlelight contains almost no blue wavelengths. It is all orange and red. This light does not suppress melatonin much. You can have candles burning at night without disrupting sleep. Electric light changed this, gave us blue wavelengths after sunset. Seasonal changes affect your clock too. Summer days are long. You get light signals for 16 hours. Your clock adjusts. You naturally stay awake longer. Winter days are short. Only 8 hours of daylight. Your clock wants more sleep. This is why seasonal depression happens. Less light means weaker clock signals. The rhythm becomes less stable. Mood follows. Light therapy helps. Bright lights in the morning. Resetting the clock. Strengthening the rhythm. Your clock uses light as truth. Whatever light says, the clock believes. This is why rotating shift work is so harmful. Your light exposure tells your clock different things each week. The clock never fully adjusts, remains confused. The best sleep happens when your light exposure matches natural patterns. Bright light in the morning, dimmer light through the day, very dim or no blue light in the evening, darkness at night. This is what your clock expects. You can use this knowledge. Want to wake earlier? Get bright light first thing in the morning, even before coffee. Step outside. Tell your clock it is time. Want to stay up later? Get bright light in the evening. Shift your clock later. Your clock is a tool. Light is how you program it. Every morning when light hits your eyes, you are resetting your internal timekeeper, synchronizing yourself to the day. It happens automatically, but understanding it lets you work with your clock instead of against it. And somewhere the sun is rising, blue light spreading across the land. Millions of circadian clocks resetting simultaneously. Time beginning again as it does every day. Light resets biological clocks. But what resets the clocks we build? What is the most accurate timekeeper we have? The answer is inside an atom, cesium-133, a silvery metal that melts just above room temperature. This element keeps time better than anything else we have discovered. An atom is mostly empty space, a nucleus at the center, electrons orbiting around it. These electrons can only exist at specific energy levels. They cannot be between levels. They must jump from one level to another. When an electron jumps between levels, it absorbs or releases energy. This energy takes the form of light, a specific frequency of light. Always the same frequency for the same jump in the same type of atom. Cesium atoms have an electron transition that scientists use as a clock. When this electron jumps, it absorbs or emits light at exactly 9,192,631,770 times per second. That number is not approximate, not rounded. It is exact. The definition of a second is now based on this number. 1 second equals 9,192,631,770 oscillations of this cesium transition. This is the most stable frequency we know. It does not change with temperature, does not change with pressure, does not change with age. Every cesium atom vibrates at exactly this rate, forever. An atomic clock uses this vibration. It shines light at cesium atoms. When the light frequency exactly matches the atomic transition, the atoms respond. They absorb the light. This tells the clock the light is at exactly the right frequency. The clock adjusts its frequency to match, locks onto the atomic vibration. Now, the clock is oscillating at exactly 9 billion times per second. It counts these oscillations. Every 9,192,631,770 oscillations equals 1 second. The accuracy is extraordinary. An atomic clock loses less than 1 second in 100 million years. If you started it at the time of the dinosaurs, it would be off by less than a minute today. This precision changed everything. GPS satellites need atomic clocks. They measure the time it takes radio signals to travel from satellite to receiver. Light travels fast, really fast. Small timing errors create large position errors. Without atomic clocks, GPS would be useless. The internet relies on atomic time. Computers worldwide synchronize to atomic clocks. This coordination lets networks function, lets timestamps be accurate, lets transactions happen in the correct order. Scientists use atomic time for experiments that require extreme precision, measuring the speed of light, testing relativity, detecting gravitational waves. These experiments need time measured to billionths of a second. Atomic clocks provide this. Multiple atomic clocks run around the world. They are averaged together to create international atomic time. No single clock is perfect, but the average of many clocks is more stable than any individual clock. This average time defines civil time, the time on your phone, on your computer, the time broadcast by radio signals, all ultimately traceable to cesium atoms vibrating in laboratories. Newer atomic clocks are even more accurate. Optical atomic clocks use strontium or ytterbium. These atoms vibrate at light frequencies, hundreds of trillions of times per second. More oscillations mean more precision. These optical clocks are so accurate, they can detect the time difference caused by height. A clock 1 centimeter higher runs slightly faster. Gravity is weaker at higher elevation. Time passes faster where gravity is weaker. The clock measures this. This seems absurd. Time running at different speeds based on height. but Einstein predicted it. General relativity says gravity warps time. The clocks prove he was right. Someday, these optical clocks might redefine the second. Replace cesium, make time even more precise. But cesium will have served well. It took us from pendulums losing seconds per day to clocks losing seconds per 100 million years. Right now, in laboratories around the world, cesium atoms are vibrating 9 billion times per second, defining what a second means, keeping time at a level of precision our ancestors could not imagine. The heartbeat of modern time, atomic, eternal, perfect. Atomic clocks measure time with perfect consistency, but your brain does not. Time feels different depending on what you are doing, how old you are, what you are paying attention to. Think back to childhood summers. They felt endless. 3 months stretched like years. You had time for everything. Long afternoons that seemed to last forever. Why did time feel so slow? Novelty. Everything was new when you were young. First time riding a bike. First time swimming in the ocean. First time staying up late. Your brain was recording all of this, making memories. Lots of memories. Memory is how your brain measures time after the fact. When you look back, your brain estimates duration by how many memories you have. More memories means more perceived time. Those summers had countless new experiences, countless memories. So they feel long in retrospect. As an adult, routine dominates. You do the same things repeatedly. Drive the same route to work. Eat the same breakfast. Follow the same schedule. Your brain stops recording all of this. Why record something you have seen 1,000 times? This makes time feel like it accelerates. Weeks pass in a blur, months vanish. Not because time actually moves faster, but because you are not forming as many distinct memories. When you look back, there is less to remember. Less memory equals less perceived time. This is why vacations feel long. You are doing new things, seeing new places. Your brain records everything. A week of vacation can feel longer than a month of routine. The memories stretch it out. Attention affects time perception too. When you focus intensely on something, time seems to slow. Athletes in the zone report time slowing down. Everything happens in slow motion. They can react to things that normally happen too fast to see. This is not time actually slowing. It is your brain processing faster, taking in more information per second, creating more detailed memories. Those extra details make the moment feel extended when you remember it. The opposite happens when you are not paying attention. Time flies. You daydream through a meeting, and suddenly an hour has passed. Your brain was not recording. No memories formed. The time seems to disappear. Fear stretches time. In an emergency, time seems to slow dramatically. A car accident that takes 2 seconds feels like it lasts 10. Your brain goes into high alert, records everything in extreme detail. The memory is so rich, it feels like more time passed. Experiments prove this. Scientists had people free fall from towers while looking at a display showing numbers. The numbers flashed too fast to normally see, but people reported seeing the numbers clearly during the fall. Their brains were processing information faster under stress. The present moment has a different perception than memory. While something is happening, boring things feel slow, exciting things feel fast. But in memory, it reverses. Boring times compress, exciting times expand. This is why waiting rooms feel eternal, but the appointment flies by. Why a boring lecture drags, but you cannot remember it later. Why the best moments of your life feel both fast and long. Fast while experiencing them. Long when remembering them. Age changes everything. Each year represents a smaller fraction of your total life. At age 10, 1 year is 10% of your life. At age 50, 1 year is 2%. This might explain why years seem to accelerate. Each one is a smaller piece of the whole. Your brain also slows its processing slightly as you age. It has less neuroplasticity, forms fewer new connections. This might make time feel faster. Less intense recording means less detailed memory, means shorter perceived time. You can slow time down, seek novelty, do new things, break routines, travel, learn new skills, force your brain to pay attention, to record, to form memories. The more memories you make, the longer life feels. Pay attention to the present. Notice details. Engage fully. This creates richer memories, makes moments expand, gives you more perceived time from the same number of hours. Time is flexible in your mind, stretches and compresses based on experience and memory. The clock measures constant seconds, but your brain experiences time as anything but constant, elastic, personal, deeply human. Your brain experiences time personally, but society needs time to be shared, agreed upon. This creates a problem when you live on a sphere. The sun cannot be directly overhead everywhere at once. When it is noon in New York, it is night in Tokyo. Each place has its own solar time, its own local noon. For thousands of years, this did not matter. People rarely traveled far. Local time was enough. Then railways happened. Trains moved faster than horses, connected distant cities. Suddenly, people needed to coordinate schedules across hundreds of miles. But every town kept its own time. Noon in one city was 11:58 in the next city, 11:54 in the city after that. Train schedules became nightmares. A train leaving at noon. Which noon? The departure city's noon, or the arrival city's noon. Passengers missed trains. Trains collided. Time needed standardization. In 1883, North America divided into 4 time zones: Eastern, Central, Mountain, Pacific. Everyone within a zone used the same time, even if the sun said different. This was revolutionary. Artificial time, chosen by convenience, not astronomy. The world followed. By 1900, most countries used time zones, each zone roughly 15 degrees of longitude wide. 24 zones for the 360 degrees around Earth. Each zone 1 hour different from its neighbours. The math is elegant. Earth rotates 360 degrees in 24 hours. That is 15 degrees per hour. So every 15 degrees of longitude, time shifts by 1 hour. Stand on one side of the boundary. It is 3 o'clock. Step across the line. Suddenly it is 2 o'clock. The boundaries are not straight lines. They follow political borders, state lines, national borders. This creates odd shapes, but it prevents a single city from having 2 different times. Everyone in the city agrees what time it is. Some time zones are offset by half hours or even quarter hours. India is 5 hours and 30 minutes ahead of universal time. Nepal is 5 hours and 45 minutes ahead. These offsets accommodate political and geographic realities. Universal coordinated time is the reference. Based on atomic clocks in laboratories worldwide, every time zone is defined as some number of hours ahead or behind this universal time. All time everywhere traceable to the same source. The international date line runs through the Pacific Ocean. Cross it eastward and you go back a day. Cross it westward and you jump forward a day. This line prevents the calendar from getting confused, keeps everyone on Earth agreeing what day it is. Time zones create strange effects. You can fly from Los Angeles to New York. The flight takes 5 hours, but you arrive 3 hours after you left local time. You traveled forward through time zones faster than the sun moved, gained time by flying east. The opposite happens flying west. A flight from Tokyo to Los Angeles takes 10 hours, but you arrive 7 hours before you left Tokyo time. You travel backward through time zones, land before you took off according to local clocks. This is not time travel, just time zones. The actual elapsed time never changes, but the local time jumps as you cross boundaries. Some people exploit this. Work in one time zone, live in another, get off work at 5, drive an hour west, cross a time zone, arrive home at 5. You gained an hour, or lost it, depending on perspective. Daylight saving time complicates everything. Some regions shift their clocks forward in summer, fall back in winter. This saves evening daylight, but creates confusion. Not all regions do this. Not all regions do it on the same dates. Time zones fracture further. The system is imperfect, arbitrary, but necessary. Without time zones, coordination across distance would be impossible. Airlines could not function. International business would collapse. The internet would struggle. Time zones are humanity agreeing to lie about what time it is, to coordinate, to synchronize, to work together across a spinning sphere. The sun might say noon, but if society says it is 3 o'clock, then it is 3 o'clock. Right now, it is every time on Earth simultaneously. Midnight somewhere, dawn somewhere else, noon, dusk, the full day happening all at once across the globe. Each zone marking its own hour, while the atomic clocks tick the same seconds underneath it all. Time zones divide the day, but what divides the month? Look up at night. The moon tells you. The moon changes shape. Not actually, but from our perspective. New moon, crescent, half, gibbous, full, then back again. This cycle takes 29.5 days, always the same, predictable as clockwork. Ancient people noticed. The moon was a calendar in the sky, no tools needed. Just look up, count the nights, know where you are in the month. The word month comes from moon. They are the same thing. One lunar cycle, the time from new moon to new moon. This is how humans measured time, longer than a day, but shorter than a year. The new moon is invisible. It rises and sets with the sun. No sunlight hits the side facing Earth. The moon is there, but you cannot see it. This marks the beginning. Days pass. A thin crescent appears at sunset. The moon is setting shortly after the sun. Each night, the crescent grows thicker. The moon sets later. It is catching up to being opposite the sun. First quarter happens 7 days after new moon. Half the moon is lit. It sets around midnight. The moon is 90 degrees away from the sun in our sky. More days. The gibbous phase. More than half lit but not yet full. The moon rises before sunset, visible in the afternoon sky, getting closer to full opposition with the sun. Full moon comes 14 to 15 days after new moon. The moon rises as the sun sets, stays up all night, sets as the sun rises. Perfect opposition. Sunlight hits the entire face we can see. Then the cycle reverses. Gibbous again, but shrinking. Third quarter. Crescent again, but facing the other direction, until the moon disappears and the cycle starts over. This rhythm governed ancient life. Many cultures started their months at new moon, others at full moon, but all used the moon to organize time beyond days. The lunar calendar has problems. 12 lunar months equal 354 days. The solar year is 365 days. They do not match. A pure lunar calendar slowly shifts through the seasons. Islamic calendar uses pure lunar months. Ramadan moves through the year, sometimes in summer, sometimes in winter. Each year 11 days earlier than the previous year. This is mathematically correct for lunar months, but disconnected from seasons. Most ancient cultures solved this by adding extra months occasionally. Leap months, when the lunar calendar drifted too far from the seasons, insert an extra month. Bring it back in sync. The Hebrew calendar still does this. The moon connects to tides. High tide happens when the moon is overhead, and again when the moon is on the opposite side of Earth. Low tide halfway between. This cycle takes about 12.5 hours. Fishermen and sailors learned to read the moon. Full moon means the highest tides. New moon also brings high tides, called spring tides, not because of the season, because the water springs high. First and third quarter bring the weakest tides, neap tides. Women's menstrual cycles average 28 days, close to the lunar month. Some cultures believed this was caused by the moon. Modern science finds no direct connection, but the similarity is striking. Two biological rhythms, both measuring similar time periods. The moon stabilizes Earth's tilt. Without the moon, Earth would wobble wildly. Seasons would be chaotic. The moon's gravity keeps our planet steady, gives us consistent seasons, consistent climate. The moon does more than mark time. It makes our time stable. We still use moon phrases. Once in a blue moon, meaning rare. A blue moon is the second full moon in a single calendar month. This happens every 2 to 3 years. Rare but regular. Honeymoon, the month after marriage, named because it was traditionally one lunar cycle. The sweet moon after the wedding. The moon is less important now for timekeeping. We have better tools. But look up. The phases still cycle, still marking time as they have for billions of years. A clock face in the sky. Nature's calendar. Visible to anyone who looks up at night. The moon measures months. But what measures the year? The seasons. Earth's longest natural rhythm. Earth tilts 23.5 degrees. This tilt is everything. It creates summer and winter, makes days long in June and short in December, gives us seasons to mark the passage of a full year. Summer happens when your hemisphere tilts toward the sun. The sun rises higher in the sky, stays up longer. More direct sunlight means more heat. Days stretch past 16 hours. Warmth accumulates. Winter is the opposite. Your hemisphere tilts away from the sun. The sun stays low. Days shrink to 8 hours. Sunlight arrives at a steep angle, spreads out, delivers less energy per square meter. Cold deepens. The equinoxes are the transition points. Spring and fall. Day and night have equal length. The sun rises exactly east, sets exactly west. 12 hours of day, 12 hours of night. The balance points of the year. The summer solstice is the longest day. The sun reaches its highest point in the sky. After this, days begin shortening. The word solstice means sun standing still. For a few days, the sun rises and sets at almost the same spot on the horizon. Then it starts moving back. The winter solstice is the opposite. Shortest day, longest night. After this, days begin lengthening. Ancient people feared the sun might continue south forever. Leave them in darkness. When the solstice passed and days started lengthening again, they celebrated. The sun was returning. Animals use seasons as a clock. Birds migrate when day length reaches a certain point. Their bodies measure the changing light, know when to fly south, when to return north. This timing is so precise that certain species arrive on almost the exact same date each year. Plants do this too. Trees sense the shortening days, know winter is coming. They stop making chlorophyll, leaves change colour, fall. The tree prepares for dormancy. Spring comes and lengthening days trigger growth. Buds form, leaves emerge, all timed by the slow change in day length. Bears hibernate based on seasons. They fatten up in fall, den in winter. Their metabolism slows dramatically. Heart rate drops. They survive months without food or water. Spring arrives and they emerge. The seasonal clock built into their biology. Agricultural societies lived by seasons. Planting time, growing time, harvest time. The year divided into work appropriate for each season. You cannot plant in winter, cannot harvest in spring. Seasons dictated what was possible. Ancient calendars tracked seasons carefully. Stonehenge aligned with the solstices. The sun rises through specific stone archways on the longest and shortest days. This alignment let people know exactly where they were in the year. Seasonal affective disorder shows how humans respond to seasons. Shorter days and less light in winter affect mood. Energy drops. Depression increases. This is not weakness. It is biology responding to seasonal signals. Our bodies still track the seasons, even though modern life tries to eliminate their effect. The tropics have minimal seasons. Day length barely changes. Temperature stays constant. But even there, seasons exist. Wet season and dry season, driven by shifting weather patterns. Life still cycles annually, even without the temperature swings. The poles experience extreme seasons. 6 months of light, 6 months of darkness. Animals there must be highly adapted. Polar bears are active in the dark winter. Seals time their breeding to the brief summer. Every species synchronized to the dramatic seasonal changes. Seasons create the concept of years. Without seasons, we would have no natural marker for a complete Earth orbit. Days are obvious, months visible in the moon, but years require noticing the subtle return of seasonal patterns. Ancient people marked years by events. The year the river flooded, the year of the great drought, the year the locusts came. These were seasonal variations, weather patterns that cycled over years, but still tied to the seasonal clock. We now know the year is 365.25 days, Earth's orbit around the sun. But this knowledge came from watching seasons return, counting the days between summer solstices, noticing the pattern. Right now, Earth is tilted, one hemisphere leaning toward the sun, the other away. Seasons happening, animals responding, plants timing their cycles, the great annual clock ticking forward through its eternal pattern. Seasons cycle yearly, but the day itself is changing, very slowly. Earth's rotation is slowing down. A day is not exactly 24 hours. It is 24 hours now, but it was shorter in the past, will be longer in the future. The change is tiny, about 1.7 milliseconds per century, but it adds up. 400 million years ago, a day was 22 hours long. The year still had 365 days, but each day was shorter. This means the year contained more days, about 410 days per year back then. We know this from fossils. Coral grows in layers, 1 layer per day. Ancient coral has more layers per year than modern coral. The count tells us how many days were in a year when that coral was alive. The moon causes this slowdown, specifically tides. The moon's gravity pulls on Earth's oceans, creates bulges of water, high tides. As Earth rotates underneath these bulges, friction happens. Water dragging on the seafloor, land dragging through water. This friction slows Earth's rotation. Think of it like brakes. Tides are constantly breaking Earth's spin, very gently, but constantly. Over millions of years, this adds up. The day gets longer. The energy does not disappear. It transfers to the moon. The moon's orbit slowly expands. The moon moves away from Earth by about 1.5 inches per year. As Earth's rotation slows, the moon drifts farther away. This has been happening since the moon formed. 4.5 billion years ago, the moon was much closer, about 15,000 miles away instead of the current 240,000 miles. That close moon created enormous tides. Days were only 4 to 6 hours long. The moon appeared huge in the sky. Tides were massive. Earth spun so fast that fierce winds circled the planet. This was a different world, barely recognizable. The moon will continue moving away. Earth will continue slowing. Eventually, in billions of years, Earth will be tidally locked to the moon. One face of Earth will always face the moon. The day will equal the lunar month, about 47 current days long. This has already happened to the moon. It is tidally locked to Earth. The same side always faces us. We never see the far side from Earth. The moon rotates once per orbit, taking the same time to spin as to orbit. This is not coincidence. Tidal forces made this happen. Leap seconds account for the slowdown. Occasionally, we add 1 second to our clocks. This keeps atomic time synchronized with Earth's rotation. Without leap seconds, noon would slowly shift, eventually arriving at midnight. The sun would disagree with our clocks. The last leap second happened in 2016. Not every year needs one. The Earth's slowdown is not perfectly regular. Sometimes the planet speeds up slightly, from earthquakes, from ice melting, from atmosphere patterns. But the overall trend is slowing. Ancient astronomers noticed something wrong with old eclipse records. Eclipses happened at times that did not match predictions. The calculations were correct, but they assumed days had always been 24 hours. Once they accounted for the lengthening day, the records made sense. This slowdown affects everything that depends on time. GPS satellites need to account for it. Long-term predictions must include it. The accumulated difference becomes significant over centuries. In 1 billion years, a day might be 26 or 27 hours long. Humans might not exist then, but whatever intelligent life remains will have more time in each day. Though they will have fewer days per year as Earth's orbit slowly expands too. The sun also affects Earth's rotation. Solar tides, much smaller than lunar tides, but present. Everything with mass affects everything else. The entire solar system is connected through gravity, all influencing each other. Time itself is not changing. A second is still a second, but Earth's relationship with time is changing. The planet is a clock that runs slower each year. So gradually, you would never notice in a lifetime, but undeniably, measurably, real. Right now, Earth spins slightly slower than yesterday. Tomorrow, it will spin slightly slower than today. The change invisible, but the accumulation over deep time transforming how many hours fit in a day. Earth's day lengthens, but something stranger happens far from Earth. Time itself runs at different speeds. Einstein discovered this. Time is not universal, not the same everywhere. Gravity affects how fast time passes. So does speed. This sounds impossible, but it is measured, proven, real. GPS satellites experience this directly. They orbit 12,000 miles above Earth. Gravity is weaker up there. Time runs faster. The atomic clocks on satellites gain about 45 microseconds per day compared to clocks on the ground. But satellites also move fast, 7,000 miles per hour. High speed makes time run slower. This effect causes the satellite clocks to lose 7 microseconds per day. Combine both effects. 45 microseconds gained from weaker gravity. 7 microseconds lost from high speed. Net gain of 38 microseconds per day. This seems insignificant, but GPS relies on extremely precise timing. Radio signals travel at the speed of light. 1 microsecond of timing error creates 1,000 feet of position error. After one day, GPS would be off by 38,000 feet, over 7 miles. Unusable. GPS must account for relativity. The satellites run their clocks slightly slower to compensate. When compared to ground clocks, they stay synchronized. Without this correction, GPS would fail within minutes. Gravity warps time. Stronger gravity means slower time. You age slightly faster on a mountain than in a valley. The difference is tiny, about 90 nanoseconds per day at 10,000 feet elevation, but measurable with atomic clocks. Time runs slower closer to massive objects. On the surface of the Sun, time runs slower than on Earth. Near a black hole, time slows dramatically. At the event horizon, time effectively stops from an outside observer's perspective. This has been tested. Scientists flew atomic clocks on airplanes, compared them to identical clocks that stayed on the ground. The flying clocks showed less elapsed time, exactly as Einstein predicted. Astronauts on the International Station age slightly slower than people on Earth. Not much, about 0.01 seconds less per year. The combination of orbital speed and weaker gravity creates this effect. If you traveled near the speed of light, time would slow dramatically for you. Travel for what feels like 1 year at 99% light speed. Return to Earth. 20 years have passed here. You have moved into Earth's future. This is real-time travel. Forward only. No paradoxes. Just the physics of high speed. Your clock runs slower. You experience less time than stationary observers. Nothing can reach the speed of light. As you approach it, time slows towards stopping. You would experience no time at all traveling at light speed, which is why light itself does not experience time. A photon emitted from a distant star arrives instantly from its own perspective, even if the journey took millions of years in our reference frame. This connects time and space. Einstein showed they are not separate. They are space-time, a 4-dimensional fabric. Mass and energy warp this fabric. Time and space bend together around massive objects. Gravity is not a force pulling. It is curved space-time. Objects follow straight paths through curved space-time. Those paths look curved to us, but in 4 dimensions, they are straight. Time is part of this geometry. This is why time runs slower in stronger gravity. Gravity curves space-time. Objects deeper in gravity, wells follow paths where time dimensions are compressed. Less time passes for them per unit of outside time. This challenges our intuition. Time feels absolute, the same everywhere, but it is not. Every clock in the universe runs at its own rate, depending on gravity, depending on motion, all relative to observers. Your head ages faster than your feet. Slightly. It is farther from Earth's center. Experiences weaker gravity. The difference is billionths of a second per lifetime, but technically real. Time is flexible, malleable, different for everyone depending on where you are and how fast you move. Yet, we all experience our own time as normal, as constant. Only comparison reveals the differences. Right now, time runs at different rates across the universe. Fast in empty space, slow near stars, slower still near black holes. Each location experiencing its own tempo. All of it relative, all of it real. Time runs at different rates in space, but also in different species. A fly experiences time differently than you do. Faster, more frames per second. Your vision has a refresh rate. You can see about 60 changes per second. Faster than that, and motion blurs together. This is why movies work. 24 frames per second fools your brain into seeing smooth motion. A fly sees much faster, about 250 frames per second. Your hand moving toward it looks slow from the fly's perspective. This is not supernatural reflexes. It is faster visual processing. The fly's brain works on a different timescale. This explains why flies are so hard to swat. You move in slow motion to them. They have time to react, to fly away. Your hand is obvious, predictable, slow. Small animals generally have faster perception. Hummingbirds see about 100 frames per second. Mice about 130. Their worlds run at higher speed than ours. Large animals are the opposite. Elephants see about 15 frames per second, slower than humans. Their world runs at a more leisurely pace. This matches their body size. Large animals move more slowly, react more slowly, experience time more slowly. The pattern holds across species. Metabolism correlates with time perception. Higher metabolism means faster perception. Small animals have high metabolic rates, fast hearts, fast breathing, fast neural processing. They live in fast forward. A mouse heart beats 600 times per minute, 10 beats per second, compared to human 60 beats per minute. The mouse experiences roughly 10 times as many heartbeats in the same objective time. From its perspective, it might be living as full a life as a human, just compressed into 3 years instead of 80. This relates to lifespan. Small animals live fast and die young. Large animals live slow and die old. But the total number of heartbeats might be similar. Roughly 1 billion heartbeats per lifetime across many species. The timescale differs. The total experience might not. Dogs predict when dinner time arrives, not with clocks, with internal timing, their circadian rhythms combined with learned patterns. A dog's sense of time is good enough to know when their owner usually comes home, wait by the door, anticipate the return. But dogs have no concept of calendar time. Today versus tomorrow. Next week versus next month. Their time exists in immediate cycles, day and night. Meal times, walk times, patterns they learn and expect. Elephants have impressive time memory. They remember watering holes visited decades ago, can recall individual humans years after meeting them once. Long-term memory spanning their long lives. Their slower perception giving them different relationship with past and future. Crows solve delayed gratification tasks. Choose a larger reward later over a small reward now. This requires understanding future time, planning. Not all animals can do this. It suggests crow perception of time extends beyond the immediate present. Some animals enter torpor, hibernation. Their metabolism drops drastically. Heart rate might go from hundreds of beats per minute to just a few. Do they experience this time? Or does consciousness pause? We cannot know, but their bodies age more slowly during torpor, as if time itself slows for them. Mayflies live for one day as adults. Do they perceive this as a full life? Their nervous systems process information at a rate appropriate for their timescale. One day might feel complete to a mayfly, while an elephant's year might feel about the same subjectively. Time perception depends on your biology, your size, your metabolism, your neural processing speed. There is no universal time experience. Each species lives in its own temporal world. Humans sit in the middle range, not as fast as flies, not as slow as elephants. Our perception of time is one of countless possibilities. Other animals experience reality at different speeds, all sharing the same objective time but perceiving it differently. This means when you watch a bird dart past, catch an insect in mid-air, that bird is processing the world 2 or 3 times faster than you. The insect even faster. They exist in temporal realities different from yours, all happening simultaneously but experienced at different rates. Right now, animals around you experience time at their own pace. Fast, slow, all valid, all real. Time is not one thing. It is as many things as there are ways to experience it. Animals experience time at different speeds. Humans do too. Not as dramatically, but measurably. Your personal time rhythm. Some people wake easily at dawn, feel energetic in morning, get tired by 9 at night. These are larks. Morning people. Their circadian clocks run slightly fast. Others struggle to wake before 9. Feel alert at midnight, could stay up until 2 in the morning without difficulty. These are owls, night people. Their clocks run slightly slow. This is genetics, not choice, not laziness. Your chronotype is largely determined before birth. The genes controlling your circadian clock have variations. These variations set your natural rhythm earlier or later. About 15% of people are strong larks. Another 15% are strong owls. The rest fall somewhere in the middle, with a bell curve centered around moderate morning preference. Your chronotype affects everything: when you think best, when you are most productive, when you get hungry, when your body temperature peaks. All of these follow your personal rhythm. A lark's body temperature rises before dawn. Cortisol floods their system. They wake naturally. By 6 in the morning, they are alert. By 10, they are at peak performance. By 8 at night, they are fading, their body preparing for sleep. An owl's temperature rises later. Cortisol comes later. They wake sluggish, need time to become functional. They hit peak performance around 2 or 3 in the afternoon. Stay strong through evening. At midnight, when larks are deep asleep, owls are still sharp. Society favors larks. School starts at 8. Work starts at 8 or 9. If you are a lark, this matches your rhythm perfectly. If you are an owl, you are fighting your biology every single day. Teenagers are naturally owls. During puberty, circadian rhythms shift later. This is why teenagers want to sleep until noon. Their bodies are running on a delayed schedule. Making them wake at 7 for school is like asking an adult to wake at 4 or 5 in the morning. This shift reverses with age. Older adults become more lark-like, wake earlier, sleep earlier. The rhythm shifts back through life stages. You cannot change your chronotype much. A strong owl forced to wake at 6 will never become a lark. They will always struggle. Their body will always resist. The best they can do is manage. Get bright morning light. Use caffeine strategically, but underneath they remain an owl. knowing your chronotype helps. Schedule important work for your peak time. If you are an owl, do not schedule crucial meetings at 8 in the morning. Your brain will not be ready. Wait until afternoon. If you are a lark, do challenging work early. By evening, your brain has passed peak. Save easier tasks for then. Do not try to do complex work at 9 at night. Your circadian clock says sleep. Fighting it is inefficient. Couples often have different chronotypes. One lark, one owl. This creates tension. The lark wants to go out for breakfast. The owl can barely function. The owl wants to watch a late movie. The lark is falling asleep. Neither is wrong. They are operating on different biological time. Shift work is hardest for strong chronotypes. If you are a lark forced to work night shift, you are fighting your biology every day. Your clock insists it is time to sleep, but work requires alertness. This conflict never resolves. Health suffers. Night owls suffer in regular society, called lazy for sleeping late, accused of poor work ethic. But their brains are genuinely not ready in the morning. They are not choosing to be slow. Their biology dictates it. Some jobs suit owls. Security work, emergency rooms, anything that happens at night. Owls thrive in these roles. Finally, their natural rhythm matches the demands. The modern world with electric light lets us somewhat override chronotype, but not completely. The underlying rhythm remains. You can force yourself awake, but you cannot force peak performance at the wrong time. Your personal time exists alongside clock time. Clock says 8 in the morning, but your body might say 5 in the morning or 11 in the morning, depending on your chronotype. Living in constant mismatch between clock time and biological time creates stress. Right now, your body has an opinion about what time it is. That opinion might differ from the clock. Both times are real, both valid. The challenge is navigating a world that respects one but not the other. Your chronotype sets when you feel alert, but memory determines how long moments feel. Time is created by remembering. Think about your last vacation. How long did it feel? Now think about last Tuesday at work. Which feels longer in retrospect? Probably the vacation, even though both might have been the same number of days. The vacation created more memories, new sights, new experiences, new information. Your brain encoded all of this. When you recall the vacation, you have many memories to review. This abundance of memory makes the time feel extended. Your brain judges duration by memory density. More memories equals more perceived time. Last Tuesday created few memories. Same routine, same tasks, same commute. Your brain stopped recording. It has seen all this before. Why waste energy encoding repetition? So when you try to remember last Tuesday, there is not much there. The day compresses, feels short, almost like it did not happen. Your brain skipped recording, so memory treats it as brief. This is why time seems to accelerate as you age. Childhood was full of firsts. First day of school, first friend, first bike, first everything. Your brain recorded intensely. Those years feel long in memory. Adulthood settles into routine. Same job, same route, same people, fewer firsts, less recording. The years compress. 10 years of routine can feel shorter than 2 years of childhood. The memory density determines perceived duration. You can slow time down, break routine, do new things, take different routes, visit new places. Your brain will start recording again, create memories. Those weeks will feel longer when you look back. Novel experiences stretch time while they are happening too. Not just in memory. Your brain processes new information more carefully, pays more attention. This intense focus makes the moment feel extended. Danger does this extremely. In an emergency, your brain records everything, every detail, ultra-high resolution memory. This creates the sensation of time slowing. Not because time actually slows, but because you are recording so much information per second. Habituation works the opposite direction. The more familiar something becomes, the less your brain records. The first time you drive a new route, it feels long. You notice every turn, every landmark. The 10th time you drive it, the route feels shorter. You have stopped noticing, stopped recording. This is why the drive to a new place feels longer than the drive back. Going there is novel. Your brain records the route. Coming back is familiar. Your brain coasts. The return trip feels shorter, even though the distance is identical. Emotional intensity increases memory encoding. Joyful moments feel extended. So do painful ones. Your wedding day, your first heartbreak. These moments created intense memories. They feel longer in retrospect than they actually were. Boredom compresses time terribly. Waiting rooms, long meetings, nothing novel happens. No emotional intensity. Your brain barely records. Hours pass with almost no memory formation. Later, those hours feel like minutes. They essentially vanished. Sleep creates a memory gap. You lose consciousness. 8 hours pass with minimal memory formation. Dreams create some memory, but far less than waking time. This is why nights feel short. You are not recording much of the experience. Memory is imperfect. It fades, changes, combines different events. This makes time perception unreliable. You might remember something as lasting an hour when it was 20 minutes, or remember 20 minutes as an hour. Your brain's judgment of duration depends on memory, which depends on attention, which depends on novelty and emotion. Mindfulness extends perceived time. When you pay attention to the present moment, you create more memory. Each moment becomes richer, more detailed. Meditation practices train this attention, make ordinary moments feel more substantial. The opposite is autopilot, going through motions without awareness, driving home and not remembering the drive. Your brain was elsewhere, no memories formed. The trip vanished from your experience. Time only exists for you through memory. The present is infinitesimally small, already past before you perceive it. What you think of as now is actually memory of a moment ago. Your entire experience of time is memory reviewing itself. This means time is constructed, built by your brain from memories. Different people remember the same event differently, so they experienced different amounts of time, even though the clock measured identically. Right now, you are forming memories, or not, depending on how much attention you are paying, how novel this moment feels. These memories will determine how long this moment feels when you look back. You are creating your perception of time right now. Memory shapes your perception of time. But rapid travel through time zones breaks something else. Your circadian rhythm. This is jet lag. Your suprachiasmatic nucleus expects consistent day-night cycles. Light at certain times, dark at certain times. This pattern has been stable for your entire life in one location. Your clock is set to it. Then you fly across time zones. Board a plane at noon. Fly east for 6 hours. Land at 6 in the evening local time. But your body thinks it is midnight. Your clock has not caught up. The local sun says evening. Your brain says middle of night. melatonin floods your system. You become exhausted, but everyone around you is still active, eating dinner, starting their evening. You are fighting to stay awake. This is jet lag, the mismatch between your internal clock and the external environment. Your body is on old time, the world is on new time. The conflict creates fatigue, confusion, difficulty thinking. It takes about 1 day per time zone to adjust. Cross 6 time zones, and your body needs roughly 6 days to fully synchronize. During those days, you are partially adjusted, neither here nor there temporally. The direction matters. Flying east is harder than flying west. Flying east means shorter days. You are trying to force your clock forward. Go to sleep before your body is ready. Wake before your body wants. Flying west means longer days. You stay awake a bit later than usual. Sleep in a bit. This is easier. Your body can tolerate delayed sleep more easily than advanced sleep. The technical names are phase advance and phase delay. Advancing your phase means shifting your clock earlier, harder. Delaying your phase means shifting later, easier. This asymmetry affects all jet lag. During adjustment, your body's rhythms are chaotic. Cortisol rises at the wrong time. Body temperature peaks off schedule. Melatonin comes too early or too late. Everything that normally synchronizes is misaligned. This affects cognition. Jet-lagged people perform poorly on mental tasks. Reaction time slows. Decision-making suffers. This is why major business negotiations after international flights are risky. Neither party is thinking clearly. Athletes experience this too. Performance drops when competing in different time zones. The body expects to be asleep or just waking. Cannot perform at the time the competition requires. Professional teams arrive days early to adjust. You can prepare for jet lag. Before traveling east, start waking earlier. Go to bed earlier. Shift your schedule gradually toward the destination time. This gives your clock a head start. The adjustment after arrival is smaller. Light exposure helps. Get bright light in the morning of your destination. This resets your clock faster. Avoid bright light in the evening. Let darkness tell your body it is night. Work with the cues. Melatonin supplements can help. Take melatonin at the destination bedtime, even if you are not sleepy. This signals your body to shift its rhythm. The hormone is a powerful time cue, but nothing eliminates jet lag completely. Your clock adjusts at its own pace. You can help it, encourage it, but not force it. The suprachiasmatic nucleus responds to consistent signals over days, not immediate commands. Frequent travelers never fully adjust. Flight attendants, pilots, business people flying across zones weekly. Their clocks exist in constant flux, never settling. This chronic misalignment has health consequences. Sleep disorders, metabolic problems, increased disease risk. Some people are more resistant to jet lag. They adjust faster. Their clocks are more flexible. Others struggle with even small time changes. Their clocks are rigid, prefer stability. Both are genetic traits. Children adjust faster than adults. Their circadian systems are still developing. More plastic. Elderly adults adjust slowest. Their clocks are set firmly. Resist change. Middle-aged adults fall between. The experience of jet lag teaches something important. Your body has its own time. That time is not optional, not negotiable. You can override it temporarily with willpower and caffeine. But the underlying rhythm remains, demanding alignment, punishing mismatch. Jet lag is your circadian clock asserting itself, reminding you that you are biological. that you run on internal time. That external time and internal time must align for you to function well. Right now, travelers are landing in new time zones. Their bodies confused, their clocks slowly adjusting. Time moving at two speeds simultaneously, clock time and body time. The gradual synchronization already beginning. Jet lag reminds us time is biological, but future clocks will be even more precise than biology, more accurate than we can imagine needing. Cesium atomic clocks are remarkable. 1 second error per 100 million years. But scientists have built something better. Optical atomic clocks. These clocks use strontium or ytterbium atoms. Instead of microwave frequencies like cesium, they use light frequencies, optical frequencies. Light oscillates hundreds of thousands of times faster than microwaves. More oscillations per second means more precision. Like a ruler with finer markings, you can measure smaller intervals. Optical clocks are accurate to 1 second in 15 billion years, longer than the universe has existed. These clocks can detect gravity. A clock 1 centimeter higher runs measurably faster. The gravitational difference is tiny, but enough for the clock to notice. This turns clocks into gravity sensors. You could map Earth's gravitational field with these clocks, find underground water, detect ore deposits, predict earthquakes, all by measuring tiny variations in how fast time passes at different locations. This seems like science fiction, but it works. Optical atomic clocks exist now in laboratories. They are too delicate for everyday use, too expensive, but they prove the principle. Time measurement has reached the point of measuring gravity itself. Quantum clocks may come next, using quantum entanglement to synchronize multiple atoms. The entangled atoms share a quantum state. Measuring one instantly affects the other, even across distance. This creates clocks that are fundamentally synchronized. Such clocks could redefine the second. Currently, 1 second is defined by cesium. In the future, it might be defined by strontium or another element. More stable, more accessible, more practical for maintaining time standards. Why does this precision matter? Most people do not need nanosecond accuracy, but technology does. GPS needs relativity corrections at the nanosecond level. Future navigation systems will need more. Quantum internet will need picosecond synchronization. Financial markets care about microseconds. High-frequency trading happens at this timescale. Being 1 microsecond faster than competitors means millions in profit. Time has become money in the most literal sense. Scientific experiments need extreme precision, testing relativity, detecting gravitational waves, measuring fundamental constants. All of this requires the best clocks we can build. Better clocks enable better physics. Some researchers envision clocks so accurate they measure time's passage at different heights on a table. The difference between the clock on the floor and the clock on the shelf. This is not practical need. This is pushing boundaries, seeing what becomes possible. Others imagine portable optical clocks, clocks you could carry, use in the field. This would revolutionize geology, navigation, fundamental research. Currently, optical clocks fill rooms, need vacuum chambers, laser cooling, major infrastructure. Miniaturization is the challenge. The future might eliminate clocks entirely for some purposes. Quantum systems can act as their own timekeepers, each quantum state marking time. Computation and timekeeping merge. No separate clock needed. Time standards will evolve. Currently, atomic time is maintained by averaging hundreds of cesium clocks worldwide. Future time might average optical clocks, different atoms, different laboratories, creating even more stable time. But for most people, time precision plateaued long ago. Your phone's clock is accurate to milliseconds, more than enough. The extra precision benefits technology, infrastructure, science, not daily life. You will never personally need picosecond accuracy, but you benefit from it. GPS works because of precise time. Internet coordination, power grid synchronization, cell phone networks, all rely on clocks you never see, maintaining time far more accurately than you need. The progression is stunning, from sundials accurate to hours, to pendulum clocks accurate to seconds, to atomic clocks accurate to nanoseconds, to optical clocks accurate to parts of a nanosecond, each generation improving by factors of thousands. Where does it end? Perhaps there is a fundamental limit, a smallest meaningful time interval, below which time itself becomes uncertain. Quantum time, where measurement affects reality. Physics suggests this limit exists, around 10 to the minus 43 seconds. Planck time. We are still 40 orders of magnitude away from that limit. Room for improvement, for clocks even more precise, for time measurement that approaches the fabric of reality itself. Right now, in laboratories, these future clocks tick, measuring time at precision that makes gravity visible, preparing for applications we cannot yet imagine. The future of time measurement, more accurate than necessary, perfect because we can. Future clocks will measure time to impossible precision, but the most important time is beyond measurement. Right now, this moment, we started with your heartbeat, that internal clock. We traveled through sundials and water, pendulums and gears, atomic vibrations and relativity, time zones and circadian rhythms, memory and perception, all the ways humans have tried to capture time. But time is not really captured by any of this. Clocks measure, they do not create. They track something more fundamental, the flow that carries us from past through present into future. Your heart beats, 1 second, another second. This continues. The only time that exists is the beat happening now. The last beat is memory. The next beat is anticipation. Only now is real. Think about this moment. You are listening, breathing, existing. This is time in its purest form. Not hours or minutes, not measured intervals, just the ongoing experience of being present. The present is impossibly thin. By the time you perceive a moment, it has already passed. What you think of as now is actually memory of an instant ago, your brain processing information that arrived milliseconds earlier. The true present is unreachable, gone before you grasp it. And yet, the present is all you have. Past is fixed. Memory, history, already written. Future is uncertain, potential, prediction. Only the present can be experienced. Only now is alive. This is why ancient philosophies emphasize presence, being here now. They understood something our clock-obsessed culture forgets. Time is not something to manage or measure. It is something to experience. Your circadian clock synchronizes you to the sun. Your heartbeat marks seconds. Your memory creates the sense of past and future. But underneath all of this is the simple fact of existing, of being, of experiencing this moment and then the next. Meditation practices often focus on breath, on heartbeat, on the present sensation. This is not mystical, it is practical. When you stop thinking about past and future, stop measuring and planning, what remains is just being, just time as it is, unadorned. The precision of atomic clocks is beautiful, The rhythm of seasons is ancient. The cycle of day and night is fundamental. All of these are real. All of these matter, but they exist to serve life, to help us coordinate, to help us understand. They are not the point. The point is the experience, the life being lived, the moments being accumulated, the journey from birth to death, measured not in years, but in heartbeats, in breaths, in experiences. You cannot save time, cannot store it for later. It passes regardless of what you do. The only choice is how you spend attention during its passage, what you notice, what you remember, how present you are. This can be peaceful. The knowledge that time flows without your control, that you cannot stop it or speed it up, that all you can do is ride it, experience it, be in it. Right now, your heart beats, your breath moves, the present unfolds. All the clocks we have built, all the time measurement we have invented, exists to help us coordinate this shared journey through time. But the journey itself is personal, individual, unique to you. Tonight, as you move towards sleep, time will change quality. Consciousness will fade. Hours will pass in what feels like instants. Your circadian clock conducting the overnight symphony of repair and restoration. Time happening to you while you are not aware. And tomorrow you will wake. The sun will rise. Light will reset your internal clock. The day will begin again, measured by all our clever devices, but experienced in the same way humans always have, moment by moment, present flowing into memory. This is time, not the measurement, the experience, not the hours on clocks, the heartbeats in your chest, the breath in your lungs, the sensation of being alive right now. Thank you for exploring time with me, for spending these moments learning how we measure and perceive and experience time's passage. I hope it brought you calm, perhaps even a different relationship with time itself. Rest well, let time carry you into sleep, and when you wake, the cycle continues. Day after day, beat after beat, the eternal rhythm, time flowing through you flowing through time, the journey we all share. And so we return to where we began, your heartbeat, that internal clock marking seconds. We explored how humans learned to measure this rhythm, to capture it in sundials and water, in pendulums and atomic vibrations. But underneath all the measurement is the simple truth. Time is what you experience, moment by moment, beat by beat. You learned how circadian rhythms conduct your biology, how light resets your clock each day, how memory shapes your perception of duration, how gravity itself bends time. All these facts connecting you to the universal flow that carries everything forward. But more than facts, I hope you found something else. A sense of peace about time. An understanding that time is not something to fight or fear. It simply is, flowing through you, carrying you, the only constant in a changing universe. If this journey brought you calm, if these quiet explorations helped you settle into rest, I would be grateful if you subscribed to Simple Science for Sleep. There are so many more wonders waiting, so many more topics that can help us find peace in understanding. Join this community of curious minds who love learning as they relax. And please, leave a comment. Tell me about your relationship with time. Are you a morning person or a night owl? What makes time feel fast or slow for you? Where are you listening from right now? I love knowing we are scattered across time zones, all finding rest together in these small wonders of science. Next time, we will explore something equally fascinating, another hidden aspect of reality, another topic that combines wonder with the kind of gentle knowledge that helps us sleep. I will meet you here again. Same peaceful place, same quiet curiosity. For now, let your heartbeat guide you into rest. That ancient rhythm still counting, still keeping time in the only way that truly matters. Your time, your beats, your moments flowing into sleep. Thank you for spending this time with me, for letting these facts about time help you find peace. Sleep well wherever you are in the world. Until next time.